Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should make your understanding of reality shimmer and shift. What if I told you that the very chair you're sitting on, the walls around you, even the stars in the distant galaxies don't truly have a fixed, definite existence until something or someone observes them? This isn't philosophy or a thought experiment about perception. This is a startling implication of the most successful scientific theory humanity has ever devised: quantum mechanics. It suggests that reality, at its most fundamental level, is not a solid, unchanging stage upon which events unfold. Instead, it's a shimmering tapestry of possibilities, and the act of observation, of thinking, might be the very needle that stitches one possibility into concrete existence. Imagine a world where a coin, once flipped, isn't heads or tails in midair, but somehow both at once, only deciding its fate the moment it lands and you glimpse it. Now, amplify that strangeness to every particle, every interaction, every potential future. This isn't just a quirky detail, it's a profound challenge to our deepest intuitions about what reality even means. It forces us to ask, if the universe is a symphony of possibilities, are we, the observers, the conductors shaping the very notes as they play out? For centuries, physics operated on the assumption that the universe was like a grand, intricate clockwork mechanism. Every gear, every spring, every lever had a precise position and momentum, and if you knew all those details, you could predict the future with absolute certainty. This worldview, championed by Isaac Newton, gave us incredible technological advances and a sense of reassuring order. But then, at the turn of the 20th century, physicists began probing the incredibly small, the realm of atoms and subatomic particles. And what they found wasn't a miniature clockwork. It was something far more bizarre, far more fluid, and far more intimately connected to us, the observers, than anyone could have imagined. The world down there at the quantum scale doesn't behave like anything we experience in our everyday lives. It defies common sense, shatters our notions of cause and effect, and whispers a radical idea. Perhaps the universe isn't just out there, independent of us. Perhaps our very consciousness plays a role in its unfolding. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin our journey into quantum reality with one of the most famous and frankly most mind-bending experiments in the history of science, the double-slit experiment. Imagine you're firing tiny projectiles like paintballs at a wall with two vertical slits. What do you expect to see on a screen behind the wall? Two clear bands of paint, right? One for each slit. Simple, predictable. Now, what if you fired waves, like ripples in a pond, at those same two slits? The waves would pass through both, interfere with each other, creating crests and troughs that result in an interference pattern of multiple bright and dark bands on the screen. This is basic classical physics. Here's where it gets genuinely strange. When you fire individual electrons, which we typically think of as tiny solid particles, at those same two slits, one at a time, what do? They don't make two bands. They create an interference pattern, just like waves. How can a single electron, fired one at a time, interfere with itself? It's as if each electron passes through both slits simultaneously, even though it's a single, indivisible particle. To truly appreciate the profound weirdness of this, let's first firmly establish our classical understanding of how the world works. In classical physics, objects are either particles or waves. A particle, like a paintball or a marble, has a definite position and momentum at any given instant. You can pinpoint exactly where it is and how fast it's moving. It follows a specific trajectory. If you throw a ball, it travels along a predictable arc. A wave, on the other hand, is a disturbance that spreads out through space, like sound waves or water ripples. It doesn't have a single definite position. It exists as a distributed pattern of energy. When two waves meet, they can add up, constructive interference, or cancel out, destructive interference, creating those characteristic interference patterns. Think of dropping two pebbles into a still pond. The ripples spread, overlap, and create a complex pattern of peaks and valleys. So that when physicists first conducted the double-slit experiment with light in the early 19th century, specifically Thomas Young's experiment in 1801, they observed an interference pattern. This was taken as definitive proof that light was a wave. Case closed. But then, as the 20th century dawned, a series of perplexing observations began to emerge. The photoelectric effect, for instance, showed that light, when interacting with matter, seemed to behave like discrete packets of energy, which Einstein famously called photons. This was the birth of the idea that light, the quintessential wave, also had particle-like properties. This revolutionary idea was dubbed wave-particle duality. Light wasn't just a wave or a particle. It exhibited properties of both, depending on how you observed it. Now, fast forward to the double-slit experiment with electrons. Electrons are definitely particles, right? They have mass, charge, and can be deflected by electric and magnetic fields. We can detect them at specific locations. So if we fire a stream of electrons at the double slits, we expect them to behave like our paintballs, passing through one slit or the other and creating two distinct bands on the screen. But as we discussed, that's not what happens. Instead, we see the unmistakable interference pattern. This implies that each electron, even when fired one at a time, somehow knows about both slits. It seems to explore all possible paths, interfering with itself, before arriving at the screen. This isn't just counterintuitive, it fundamentally breaks our classical understanding of what a particle is. A particle is supposed to be localized, not spread out like a wave, simultaneously traversing multiple paths. This is where the experiment takes its most dramatic, mind-bending turn, and where the core concept of reality not being fixed until observed truly emerges. Scientists, naturally perplexed by electrons appearing to be in two places at once, decided to investigate. They set up a detector, a tiny light source or a sensitive sensor, right next to one of the slits, specifically designed to observe which slit each electron passed through. The idea was simple. If we know which path the electron took, then it can't be interfering with itself, and the interference pattern should disappear. And here's the kicker. It did. The moment physicists tried to observe which slit the electron went through, the interference pattern vanished. Instead, they saw two distinct bands on the screen, just like the paintballs. The electrons suddenly behaved like classical particles, choosing one slit or the other, and no longer interfering with themselves. Think about this for a moment. The mere act of looking at the electron, of attempting to gain information about its path, fundamentally changed its behavior. It's not that the detector disturbed the electron in a classical sense, like nudging a ball off course. Even with the most delicate minimal interaction designed to reveal its path, the quantum nature of the electron shifted. Before observation, it behaved like a wave, a spread-out probability blur simultaneously traversing both slits. After observation, it behaved like a particle choosing a single path. This suggests that the electron didn't have a definite path, or even a definite state of being a particle or a wave, until it was observed. Its reality was, in a very real sense, undetermined. This phenomenon is often described by the concept of a wave function. Before observation, a quantum particle isn't at a specific point. It's described by a wave function, which is a mathematical representation of all the possible states the particle could be in, along with the probabilities of finding it in each of those states. In the double-slit experiment, the electron's wave function spreads out, passing through both slits as a wave of probability. It's in a superposition of states, simultaneously in multiple places, or taking multiple paths until something forces it to choose. The act of observation or measurement is what causes this wave function to collapse, forcing the particle to settle into one definite state. It's as if the universe is holding its breath, presenting all possible realities, and only exhales a single concrete reality when we interact with it. This isn't just about electrons, protons, neutrons, atoms, and even small molecules have been shown to exhibit this wave-particle duality and observation-dependent behavior. The implications are profound. It means that at the most fundamental level, reality isn't a fixed, objective backdrop. It's a dynamic, probabilistic canvas where possibilities exist until an interaction, an observation, brings one specific outcome into being. This leads to the radical question at the heart of our journey. If the universe is a superposition of possibilities until observed, what exactly constitutes an observation? Does it require consciousness? Does it require a human mind? Or is any interaction, any measurement enough to collapse the wave function? These are questions that continue to puzzle physicists and philosophers alike. But the experimental evidence for the double-slit phenomenon is undeniable. The universe, it seems, is far more participatory than we ever imagined. So we've peered into the strange world where particles are waves, and where the act of looking changes what's real. The electron, before it's measured, seems to occupy all possible paths simultaneously, existing as a blur of potential. It doesn't have a definite reality until an observation forces it to pick one. But this isn't just about position. If a particle doesn't have a definite position until observed, what about its speed, its momentum? Can we know both precisely? The answer, as we'll discover in our next chapter, is a resounding no. This fundamental limitation on what we can know about a quantum particle, a limitation not due to our instruments, but to the very fabric of reality itself, is encapsulated in one of the most iconic and profound principles of quantum mechanics, the uncertainty principle. It's a principle that will deepen our understanding of just how truly probabilistic and indeterminate the quantum universe really is. Welcome back to Dreamy Science, where we continue our mind-bending journey into the heart of quantum reality. In our last chapter, we peeled back the layers of the double-slit experiment, witnessing the astonishing truth that particles, like electrons and photons, don't just exist. They perform a ghostly dance, existing as a probability blur, until the very act of observation forces them to pick a single reality. The universe, it seems, isn't just there waiting to be seen. It's actively participating in its own creation, moment by moment. But if observation is so powerful, what is an observation? Does it require a conscious mind? Or is any interaction enough to collapse that shimmering wave function of possibilities? These are some of the deepest questions in science, and we're going to keep exploring them. Today, we're diving even deeper into the quantum weirdness, introducing another cornerstone of this bizarre reality: Heisenberg's uncertainty principle. Imagine, if you will, that you're trying to describe something as simple as a chair. You can tell me its height, its width, its colour, its material. You can know all these things simultaneously with incredible precision. Classical physics, the world of Newton, and predictable clockwork mechanisms promised us that with enough information, we could know everything about anything. From the smallest grain of sand to the furthest galaxy, the universe was a giant, intricate machine, and we just needed to figure out all the gears. Then came the quantum revolution, and with it, a young German physicist named Werner Heisenberg. In 1927, Heisenberg dropped a bombshell that fundamentally shattered this classical dream of a perfectly knowable universe. He wasn't talking about chairs, of course, but about the subatomic realm, the very fabric of existence. And what he discovered was truly astonishing. Heisenberg's uncertainty principle states unequivocally that there are certain pairs of properties of a quantum particle that you simply cannot know with perfect precision at the same time. The more accurately you measure one property, the less accurately you can know the other. It's not a limitation of our instruments, mind you. It's a fundamental law of the universe itself. The most famous pair of these complementary variables is a particle's position and its momentum. Momentum, for those who need a quick refresher, is essentially a measure of mass times velocity, how fast something is moving and in what direction. So what Heisenberg revealed is this: you cannot simultaneously know both the precise location and the precise speed and direction of a quantum particle. Let's try an analogy. Imagine you're trying to photograph a tiny superfast hummingbird. If you want to get a clear, sharp image of its exact position, you need a very fast shutter speed. But with that fast shutter, the wings become a blur, and you lose information about its precise motion, its momentum. Conversely, if you want to capture the graceful arc of its flight, showing its precise momentum, you might use a slower shutter speed, which blurs its exact position at any given instant. This analogy, while helpful, still falls short because it implies the hummingbird has a precise position and momentum, and our camera is just too clumsy to capture both. But in the quantum world, it's far more profound than that. The particle doesn't have a definite position and a definite momentum simultaneously until you measure it. It exists in a state of inherent fuzziness, a probability blur until observation forces it to choose. So why can't we know both? Let's go back to our quantum electron. To see an electron, to determine its position, we have to interact with it. We might shine a light on it, that is, hit it with a photon. But remember from chapter 1, photons aren't just waves. They're also particles with momentum. When that photon hits our electron, it gives the electron a little kick. This kick changes the electron's momentum. So by precisely measuring its position, we've fundamentally altered its momentum. Conversely, if we want to precisely measure the electron's momentum, how fast and in what direction it's moving, we might need to observe it over a longer period or with a less energetic interaction. But by doing so, we lose precision about its exact location at any single moment. It's a cosmic game of whack-a-mole where every time you try to pin down one aspect, the other slips away. This isn't just about the disturbance caused by the measurement itself, though that's part of it. Heisenberg's principle goes deeper. It suggests that these properties don't exist with definite values until they are measured. Before measurement, the particle exists as a potential, a spectrum of possibilities for both position and momentum, governed by its wave function. The act of observation, the interaction, collapses. that wave function, forcing the particle to manifest one of those possibilities. Think about it. Before you look at a quantum particle, it doesn't have a single fixed position or a single fixed momentum. It's a cloud of potential, a superposition of all possible positions and all possible momenta. When you observe it, you're not just finding out what its properties are. You are, in a very real sense, creating them by forcing the particle to settle into one specific state. This is why the uncertainty principle is so revolutionary. It tells us that the universe, at its most fundamental level, isn't deterministic. It's not a giant, predictable clockwork machine where every cause leads inevitably to a specific effect. Instead, it's inherently probabilistic, governed by chances and possibilities. There is a fundamental, irreducible fuzziness at the heart of reality. For centuries, the scientific ideal, championed by figures like Isaac Newton and later Pierre-Simon Laplace, was that if you knew the exact position and momentum of every particle in the universe at one instant, you could, in principle, predict the entire future of the universe. This was the dream of determinism, a universe where free will might be an illusion, and everything was preordained. Heisenberg's uncertainty principle shattered that dream. It declared that such perfect knowledge is fundamentally impossible. We can never know all the initial conditions of the universe with infinite precision, because the very act of trying to know them would alter them. The universe, therefore, cannot be perfectly predicted. Chance and probability are not just reflections of our ignorance. They are woven into the very fabric of existence. This has profound implications. It means that the quantum world is not merely weird, it's fundamentally unpredictable. We can calculate the probabilities of certain outcomes, but we can never say with absolute certainty what a single particle will do. It's like flipping a quantum coin. You know there's a 50-50 chance of heads or tails, but you can't predict the actual outcome until it lands. And in the quantum realm, the coin is still spinning, existing as both heads and tails, until you look at it. Beyond position and momentum, a universal principle. It's important to understand that the uncertainty principle isn't limited to just position and momentum. It applies to other pairs of complementary variables as well, such as energy and time. For instance, the more precisely you define the energy of a quantum system, the less precisely you can define the time over which that energy is possessed. This is incredibly important for phenomena like virtual particles, which can pop into existence from seemingly nothing, borrowing energy for a fleeting moment before disappearing, all thanks to the energy's time uncertainty. What does this all mean for us, observing this quantum spectacle from our macroscopic world? It means that the stuff we are made of, the atoms, the electrons, the photons, are not tiny solid balls with definite properties. They are shapeshifters, existing in a realm of potential, a shimmering tapestry of possibilities, until something, an interaction, an observation, forces them into a specific state. The universe isn't a fixed objective backdrop against which events unfold. It's a dynamic, probabilistic, and fundamentally indeterminate place at its core. And our interaction with it, even at the most basic level of measurement, plays an undeniable role in shaping the reality we perceive. So we have wave-particle duality, superposition, wave-function collapse, and now the uncertainty principle. Each concept, more mind-bending than the last, points to a universe that defies our everyday intuition. The more we try to grasp its fundamental nature, the more elusive and astonishing it becomes. But this isn't the end of the quantum story. If particles don't have definite properties until we look, and if our observation fundamentally alters them, what happens when two particles become entangled, intimately linked in a way that defies distance and classical logic? What if the universe isn't just locally weird, but globally interconnected in ways we can barely comprehend. Next time on Dreamy Science, we're going to explore quantum entanglement, a phenomenon so bizarre that even Albert Einstein famously called it spooky action at a distance. Get ready to have your mind truly blown as we discover how particles can be inextricably linked, no matter how far apart they are, sharing a single, unified quantum fate. Don't forget to hit that like button and subscribe to Dreamy Science for more journeys into the fascinating world of scientific wonder. Drop a comment below and tell us, how does the uncertainty principle challenge your deepest intuitions about reality? We love hearing your thoughts. See you next time, fellow explorers. Welcome back, fellow explorers of the universe, to Dreamy Science. If you've been with us since the beginning, you've already taken a mind-bending journey into the heart of quantum reality. We've unraveled the double-slit experiment, where particles behave like ghostly waves until observed, collapsing from a probability blur into a definite state. We've grappled with Heisenberg's uncertainty principle, learning that the very act of measuring one property of a particle fundamentally alters another, proving that some aspects of reality simply don't exist with definite values until we look. We've seen that the universe at its most fundamental level isn't the predictable clockwork machine classical physics once envisioned. Instead, it's a dynamic probabilistic realm, a shimmering tapestry of possibilities, waiting for interaction to solidify its form. But what if I told you that the quantum weirdness doesn't stop there? What if I told you that particles once linked can somehow share information instantly, no matter how far apart they are? Prepare yourselves, because today we're diving into a phenomenon so bizarre, so counterintuitive that even Albert Einstein, one of the greatest minds in human history, famously dismissed it as spooky action at a distance. We are talking, of course, about quantum entanglement. The impossible connection. A cosmic dance. Imagine two coins. You flip them both into the air, catch them, and then, without looking, place one in a box and send it to a friend on the other side of the galaxy. You keep the other coin. Now, before you look at your coin, what state is it in? Heads or tails? Classically, it's either one or the other. You just don't know which. The same goes for your friend's coin. When you finally peek at your coin, you see heads. You now know instantly that your friend's coin light years away must be tails. This is simple correlation based on the fact that the coins had definite states from the moment they landed in your hands. But quantum entanglement is profoundly different. In the quantum realm, before you look at your coin, let's call it a quantum particle like an electron, and its state is its spin up or down, it doesn't exist as either heads or tails. Instead, it exists in a state of superposition, a probability blur, where it's both heads and tails simultaneously. Remember that from the double-slit experiment? Now imagine we entangle two such quantum particles. Let's say we have two electrons, A and B. When we entangle them, we link their fates in such a way that they become a single unified quantum system, even if they drift light years apart. Their individual states, their spins, remain undefined, existing in superposition. Electron A isn't spin up or spin down, it's both. The same goes for electron B. But here's the kicker, their combined state is perfectly correlated. If electron A is spin up, electron B must be spin down. If A is spin down, B must be spin up. They are a pair, but their individual identities are still fuzzy. Now, you take electron A and fly to Alpha Centauri. Your friend stays on Earth with electron B. When you finally decide to measure the spin of electron A, say you find it spin up. At that exact instant, electron B, back on Earth, collapses from its superposition and instantly takes on the state of spin down. No matter the distance, the act of observing one particle instantly determines the state of its entangled partner. It's as if they were never truly separate. This isn't about two coins that already had definite but unknown states. This is about two particles that don't have definite states until one of them is observed, and that observation instantly influences the other, regardless of the vast cosmic gulf between them. It's truly mind-bending. This idea of instantaneous influence across vast distances deeply troubled Albert Einstein. He, along with his colleagues Boris Podolsky and Nathan Rosen, proposed what became known as the EPR paradox in 1935. They argued that if quantum mechanics was a complete description of reality, then entanglement implied either 1. Non-locality. Information could travel faster than the speed of light, which violates Einstein's theory of relativity. 2. Incompleteness. Quantum mechanics was incomplete, and there must be hidden variables, predetermined properties that the particles possessed all along even if we couldn't measure them. In this view, the particles already knew their states like our classical coins, and the measurements simply revealed what was already there. This would preserve the idea of a local, deterministic reality. Einstein, a staunch believer in a universe governed by local causes and effects, favoured the hidden variables explanation. He famously declared, "God does not play dice with the universe," expressing his discomfort with the probabilistic and seemingly non-local nature of quantum mechanics. For him, the idea that a particle's reality was fundamentally undefined until observed, and that distant particles could instantly influence each other, was anathema to common sense and the principles of local realism. The Bell test, proving the spookiness. For decades, the EPR paradox remained a thought experiment, a philosophical debate. Could there be hidden variables, or was quantum mechanics truly non-local? Enter John Stuart Bell. In 1964, Bell devised a brilliant theoretical framework now known as Bell's theorem. He showed that if hidden variables did exist and reality was truly local, meaning particles only influence their immediate surroundings, then the correlations between entangled particles would have a certain statistical limit. However, if quantum mechanics was correct and entanglement was genuinely non-local, then the correlations would exceed that limit. Bell's theorem transformed the philosophical debate into an experimentally testable hypothesis. And that's exactly what physicists set out to do. Over the years, a series of increasingly sophisticated experiments, starting with John Clauser in the 1970s, and most definitively by Alain Aspect in the 1980s, and many others since, closing various loopholes, consistently confirmed the predictions of quantum mechanics. They measured the correlations between entangled particles and found, time and time again, that these correlations violated Bell's inequality. What does this mean? It means there are no hidden variables. It means that the particles do not have predetermined states before they are measured. It means that the act of observation truly does collapse the wave function of both entangled particles simultaneously, regardless of the distance separating them. Einstein's spooky action at a distance was not just a theoretical oddity. It was experimentally verified reality. This is where it gets truly profound, my friends. Entanglement shatters our deepest intuitions about space, time, and causality. If two particles separated by light years are intrinsically linked, and the measurement of one instantly determines the state of the other, what does that say about the fabric of reality itself? It suggests that the universe, at its most fundamental level, is not a collection of independent, isolated objects. Instead, it's an interconnected, holistic system where distant events can be profoundly correlated without any apparent local cause or effect. It reinforces the idea we've been exploring. Reality isn't fixed and objective, waiting for us to merely uncover it. Instead, it's a dynamic, participatory process. The probability blur of entangled particles only resolves into definite states when an observation is made. And that observation, that looking, that interaction, doesn't just reveal a pre-existing fact. It actively participates in creating that fact for both particles instantaneously. Does this mean we can send messages faster than light? Unfortunately, no. While the collapse of the wave function happens instantly, you can't control the outcome of your measurement. If you measure your electron as spin up, your friend's electron instantly becomes spin down. But you couldn't choose spin up to send a specific message. The outcome of your measurement is still fundamentally random and probabilistic, determined only at the moment of observation. You still need to use classical, slower-than-light communication, like a phone call or email, to tell your friend what you measured so they can confirm their particle's state. So, no FTL communication, but undeniably FTL correlation. While entanglement sounds like something out of science fiction, it's not just a philosophical curiosity, it's the bedrock for a whole new generation of technologies. Quantum computing. Entangled particles can process information in ways classical computers can't even dream of. By leveraging superposition and entanglement, quantum computers could solve problems currently intractable, revolutionizing fields from medicine to materials science. Quantum cryptography. Entanglement allows for absolutely secure communication. If anyone tries to eavesdrop on an entangled pair used for encryption, the act of observation immediately breaks the entanglement, alerting the communicating parties. It's truly unhackable. Quantum Internet. Imagine a network where information is transmitted not just securely, but with unprecedented efficiency, across vast distances, connecting quantum computers around the globe. So this spooky action at a distance isn't just a bizarre quirk of the universe. It's a powerful tool that humanity is just beginning to harness. We started this journey asking, are you creating the universe by thinking? We've seen that at the quantum level, particles don't have definite properties until they are observed. We've seen that our measurement choices influence what properties manifest. And now, with entanglement, we see that this influence is not confined by space. It's a non-local, instantaneous connection that binds the universe together in ways we are only just beginning to comprehend. The universe isn't a collection of independent parts, it's a deeply interconnected whole. And your interaction with it, your act of observation, your consciousness itself, plays a crucial active role in shaping the reality that unfolds. This isn't just about tiny particles anymore. The implications ripple outwards, challenging our very understanding of existence. If the universe is fundamentally interconnected, and observation is key to defining reality, what constitutes an observer? Does it have to be a human consciousness? Or can it be any interaction, any measurement device? These are the profound questions that continue to puzzle physicists and philosophers alike. And they lead us directly into our next chapter, where we'll delve even deeper into the nature of observation itself and the truly mind-bending possibility that consciousness might be more central to the fabric of reality than we ever dared to imagine. Don't forget to hit that like button, subscribe to Dreamy Science for more cosmic adventures, and drop a comment below with your thoughts on entanglement. Does it make you feel more connected to the universe, or just more confused? We want to hear from you. Join us next time as we ask, what is an observer anyway? You won't want to miss it. Welcome back to Dreamy Science, where we journey into the most mind-bending corners of reality. If you've been with us, you know we've already plunged into the strange world of quantum mechanics, where particles dance as ghostly waves, properties remain fuzzy until measured, and distant partners share an impossible instantaneous connection. We've unravelled the double-slit experiment, grappled with Heisenberg's uncertainty principle, and marvelled at the spooky action at a distance of entanglement. But as we closed our last chapter, a monumental question lingered, a shadow stretching across all our quantum revelations. What exactly is an observation? What constitutes the act that collapses a particle's shimmering tapestry of possibilities into a single definite reality? Does it require a conscious mind, or is any interaction sufficient? This isn't just a philosophical musing, it's the very crux of understanding if you are indeed creating the universe by thinking. We've seen that a quantum particle exists in a superposition of states, a blur of possibilities, until it's observed. But what does observed truly mean? Is it merely a photon bouncing off an electron, a stray particle interacting with another? Or does something more profound, perhaps even conscious, need to be involved? For a long time, and even today for many physicists, the simplest answer is that any interaction is enough. If an electron previously existing as a wave of probability happens to interact with another particle or a detector, or even just the ambient environment, that interaction is considered an observation. It's like trying to keep a secret in a crowded room. The moment you whisper it, even to yourself, someone else might overhear, and the secret is out. In the quantum realm, the secret is the particle's indeterminate state, and that overhearing is any interaction. This idea leads us to a concept known as decoherence. Imagine a fragile quantum system like an electron in superposition perfectly isolated. It can maintain its wave-like probabilistic nature indefinitely. But in the real world, nothing is truly isolated. Our universe is a bustling, chaotic place filled with countless particles, photons, and fields constantly interacting. Decoherence suggests that these constant interactions with the environment effectively observe the quantum system. Think of it this way: a quantum particle's wave function, its probability blur, is incredibly delicate. When it interacts with even a single photon from its surroundings, that photon carries information about the particle's state. Then that photon interacts with another, and another, spreading this information throughout the environment like ripples in a pond. Before you know it, the particle's quantum state is inextricably entangled with the vast, complex state of its environment. This entanglement with the noisy environment effectively washes out the quantum superposition, forcing the particle to pick a definite state. The environment, in essence, acts as a colossal, omnipresent observer. Decoherence is a powerful and elegant explanation for why we don't see everyday objects existing in superpositions. Why doesn't your coffee mug exist in a quantum blur of both on the table and floating in the air? Because the mug is constantly interacting with billions of air molecules, photons, and even gravitational fields. Each of these interactions serves as a tiny measurement, collapsing any potential superposition faster than you can blink. Decoherence helps us understand the transition from the bizarre quantum world to our familiar classical reality. So problem solved, right? Observation is just any interaction, and decoherence explains why the quantum weirdness stays confined to the subatomic realm. Well, not quite. This is where the measurement problem rears its head, one of the deepest and most enduring puzzles in quantum mechanics. If everything, at its most fundamental level, is quantum, meaning the atoms that make up our measuring devices, our eyes, our brains, and even the environment itself, are all ultimately governed by quantum rules. Then what makes a measurement truly classical? If the measuring device is also just a collection of quantum particles, why doesn't the entire system, the particle plus the device plus the observer, simply remain in a larger, grander superposition? Why does the wave function actually collapse? Where does the classical cut happen? This is where things get truly bizarre, and where the question of consciousness re-enters the stage with a dramatic flourish. To highlight this absurdity, the brilliant physicist Erwin Schrödinger, in 1935, proposed a thought experiment that has haunted quantum physicists and philosophers ever since. Schrödinger's cat. Imagine, if you will, a steel box. Inside this box we place a cat, a living, breathing cat. Also inside the box is a diabolical device, a vial of deadly poison, a Geiger counter, and a single radioactive atom. This atom has a 50-50 chance of decaying within the next hour. If it decays, the Geiger counter detects it, which triggers a hammer to smash the vial, releasing the poison and killing the cat. If the atom does not decay, the cat lives. Now, from a classical perspective, after an hour, the cat is either dead or alive. We just don't know which until we open the box. Simple, right? But quantum mechanics, specifically the principle of superposition, forces us into a far more unsettling conclusion. According to quantum theory, until the radioactive atom is observed, it exists in a superposition of both decayed and not decayed. It's a blur of possibilities. And here's the kicker. Because the cat's fate is inextricably linked to the atom's state, the cat too must exist in a superposition. Until someone opens the box and observes its contents, the cat is, astonishingly, both dead and alive simultaneously. Our common sense screams against this. A cat cannot be both dead and alive. It's an absurd macroscopic manifestation of quantum weirdness. Schrödinger himself devised this thought experiment to illustrate what he saw as the ridiculous implications of the Copenhagen interpretation of quantum mechanics, which posits that a system remains in superposition until observed. He believed it exposed a flaw, a limit where quantum rules could apply. But the thought experiment, instead of disproving superposition, only deepened the mystery of the observer. If the cat is truly in a superposition of dead and alive states, what does it take to collapse that wave function? Is it merely the interaction of the atom with the Geiger counter? But the Geiger counter is made of atoms too, and those atoms are quantum. Does the entire box and its contents remain in superposition until we open it and consciously look inside? This brings us back to the radical idea that a conscious observer might be necessary for wave function collapse. Some physicists, most notably Eugene Wigner, seriously considered this. If consciousness is required, it suggests that reality itself is not fully formed or definite until a conscious mind interacts with it. Imagine the profound implications. What was the state of the universe before conscious life evolved? Was it all just a vast, uncollapsed superposition? And what about the parts of the universe we can never observe? Do they truly exist in a definite state? This interpretation places consciousness at the very heart of reality creation, an idea that resonates deeply with spiritual and philosophical traditions, but one that many mainstream physicists find deeply uncomfortable. It's hard to reconcile with the idea of an objective, independent universe. However, the majority of physicists today lean towards explanations like decoherence as the primary mechanism for wave function collapse, trying to avoid the necessity of a conscious observer. They argue that the sheer complexity and constant interaction of any macroscopic system with its environment is enough to rapidly collapse superpositions effectively observing itself into a definite state long before a human eye ever gets involved. The cat in this view interacts with the air molecules, the box walls, its own fur, its internal organs. All these interactions cause decoherence, quickly pushing it into either the dead or alive state, even before you peek. Yet even with decoherence, the fundamental measurement problem persists. At what precise point does the quantum blur definitively become classical reality? The boundary remains elusive, forcing us to constantly reevaluate our deepest intuitions about existence. The mystery of the observer is not just a footnote in quantum mechanics. It is a central defining challenge. It compels us to ask, is reality something that exists independently of us, waiting to be discovered? Or is it something we actively, perhaps even unconsciously, participate in shaping simply by the act of looking? This question, the very heart of our series, pushes us to the edge of what science can currently tell us. It forces us to confront the limitations of our classical understanding and to consider that our role in the universe might be far more active, far more fundamental than we ever dared to imagine. In our next chapter, we'll explore some of the most prominent and mind-bending interpretations that physicists have devised to try and make sense of these quantum paradoxes. From parallel universes where every possibility is realized, to a reality where information is key, we'll delve into the various ways scientists attempt to resolve the measurement problem and the enigma of the observer. So, if you're as fascinated as we are by this journey into the nature of reality, hit that like button and subscribe to Dreamy Science for more. And tell us in the comments below, do you think consciousness plays a role in shaping reality, or is it all just physical interactions? We can't wait to hear your thoughts. Until next time, keep dreaming, keep questioning, and keep exploring the amazing universe we all share. Welcome back, curious minds, to Dreamy Science. We've journeyed deep into the quantum realm, unraveling the bizarre behaviors of particles that defy our everyday intuition. We've seen them exist as waves and particles simultaneously, become inextricably linked across vast distances, and refuse to settle on a definite state until, well, observed. But as we grappled with Schrödinger's poor cat and the persistent measurement problem in our last chapter, a profound question hung in the air. What is an observer? Is it a camera? A Geiger counter? Or is there something more to it? What if in the grand cosmic drama you are not just a spectator, but an active participant? What if your very consciousness plays a role in solidifying the shimmering tapestry of possibilities into the concrete reality we experience? This isn't just philosophical musing. It's a question that has pushed some of the brightest scientific minds to the very edge of what we thought possible, forcing us to confront interpretations of quantum mechanics that are, frankly, as mind-bending as the phenomena themselves. Let's rewind to the lingering question from Chapter 4. If everything is fundamentally quantum, and interactions with the environment decoherence cause wave functions to collapse, where does the classical cut truly happen? If a quantum system interacting with another quantum system simply creates a larger entangled quantum system, then the entire universe, in theory, should remain in a vast superposition of possibilities. Yet here we are, experiencing a single definite reality. This is where the idea of consciousness steps onto the stage, not just as a passive recipient of reality, but as an active shaper of it. Pioneers like Eugene Wigner, a Nobel laureate in physics, openly contemplated this. He proposed that consciousness itself might be the ultimate observer that collapses the wave function. Think about that for a moment. It's not the camera or the Geiger counter, or even the cat's brain that collapses the superposition. It's the conscious awareness of the outcome. If this consciousness causes collapse, CC interpretation were true, it would mean that before a conscious mind perceives an event, that event exists in a probabilistic haze, a superposition of all possible outcomes. It's only when you, or any conscious being, become aware of it that one specific outcome is plucked from the infinite possibilities and made real. Consider the implications. If a tree falls in the forest and no conscious being is there to hear or perceive it, does it make a sound? According to this interpretation, not just the sound, but the act of falling itself, might exist in a superposition until a conscious mind interacts with the information. Your very act of looking at the world, of thinking about it, would be fundamental to its existence as you perceive it. You wouldn't just be observing reality, you would be, in a very real sense, participating in its creation. This is a profoundly personal and radical idea. It places consciousness not as an emergent property of complex matter, but as a fundamental ingredient of the universe, perhaps even a prerequisite for reality to solidify. It suggests that the universe isn't just out there waiting to be discovered, but that it needs an interactive mind to actualize its potential. But as you might imagine, this interpretation raises more questions than it answers for many physicists. What is consciousness then? Where does it come from? Does a bacterium count? A complex AI? And what happened before conscious life evolved? Was the universe just a giant uncollapsed wave function for billions of years? These are deep, almost spiritual questions that push the boundaries of science and philosophy. Because the consciousness causes collapse idea feels so, unscientific to many, physicists have explored other ways to solve the measurement problem without invoking a special role for consciousness. One of the most compelling and equally mind-bending alternatives is the many worlds interpretation, MWI, first proposed by Hugh Everett III in 1957. MWI offers an elegant, albeit extravagant solution. What if the wave function never collapses? What if all possible outcomes of a quantum measurement actually occur? Here's the core idea. Whenever a quantum event with multiple possible outcomes occurs, say an electron could spin up or spin down, the universe doesn't choose one. Instead, the universe sets, or rather decoheres into separate non-interacting branches, with each branch representing a different outcome. In one universe, the electron spins up. In another, a parallel universe, the electron spins down. And it's not just the electron that splits. You, the observer, also split. If you observe the electron spinning up, there's a version of you in that universe. And simultaneously, in another universe, there's another version of you observing the electron spinning down. Every quantum decision, every probabilistic flicker, every possible path leads to a new, branching universe. Imagine you're flipping a coin. In your classical world, it lands heads or tails. But in the many worlds interpretation, when that coin is flipped, the universe splits. In one universe, the coin lands heads, and you observe it. In another, parallel universe, the coin lands tails, and a different version of you observes that. And you are completely unaware of your other selves because these universes, once branched, no longer interact. They are distinct, parallel realities, coexisting but forever separated. This interpretation completely sidesteps the measurement problem. There's no mysterious collapse because every possibility is realized. The wave function, which describes all potential states, simply continues to evolve, encompassing an ever-growing number of parallel realities. It's a universe of infinite possibilities, all happening right now, just in different inaccessible branches. So which view is correct? Are you the unique conscious entity collapsing a single reality, or one of countless versions of yourself living out every possible outcome across an infinite multiverse? Both interpretations offer profound, almost dizzying answers to the quantum riddle. The consciousness causes collapse view places immense power and responsibility on your awareness, suggesting a deep, almost magical connection between mind and matter. It implies a universe that is, in some sense, awaiting your conscious input to become definite. It challenges us to rethink the very nature of consciousness and its place in the cosmos. If this is true, then your thinking isn't just internal processing, it's an active fundamental force in the universe. The many worlds interpretation, on the other hand, removes the burden of collapse from consciousness entirely. It paints a picture of a universe that is deterministic in its branching, with every potential path realized. Your choices, your observations don't create a specific reality from possibilities. They simply determine which branch of reality you find yourself in. It's a universe of infinite what-ifs all playing out simultaneously. While it doesn't give your consciousness a special role in collapsing reality, it does force you to contend with the idea of countless versions of yourself, each experiencing a different life based on every quantum uncertainty. It's crucial to understand that neither of these interpretations has been definitively proven or disproven. They are frameworks that allow physicists to make sense of the same bewildering quantum data. They are different stories we tell ourselves to explain the same fundamental truths revealed by experiments. The math works for both. The experiments are consistent with both. The choice often comes down to which set of philosophical implications you find more palatable or less problematic. Do you prefer one universe with a mysterious conscious observer, or an infinite number of universes without one? Regardless of which interpretation resonates more with you, one thing is abundantly clear. Quantum mechanics shatters our deepest intuitions about reality. The universe isn't a fixed, objective backdrop against which events unfold. It's dynamic, probabilistic, and deeply intertwined with the act of observation. Whether you are actively shaping a single reality or navigating one of countless branching realities, your relationship with the universe is far more intimate and profound than classical physics ever dared to imagine. We've moved from particles that refuse to settle to connections that defy distance, to the very nature of observation itself. And now we're standing at the precipice of interpretations that challenge our sense of self, our free will, and the very fabric of existence. In our next chapter, we'll dive even deeper into these profound implications, asking what this quantum reality means for our choices, our destiny, and the ultimate question that started this journey: are you creating the universe by thinking? Stay curious, stay dreamy, and don't forget to hit that like button and subscribe for more mind-bending science. Drop a comment below and let us know which interpretation of quantum mechanics blows your mind the most. Welcome back, curious minds, to Dreamy Science, where we continue our mind-bending journey into the heart of quantum reality. In our last chapter, we wrestled with the profound measurement problem and explored two radical interpretations that attempt to solve it: the idea that consciousness causes collapse and the sprawling, ever-branching universe of the many worlds interpretation. We left off with the tantalizing notion that the relationship between the observer and the observed universe is far more intimate and participatory than classical physics ever dared to imagine. But what does this intimacy truly mean for you, for your experience of reality, and for that provocative question that headlines our entire series: are you creating the universe by thinking? Today we dive headfirst into these questions, exploring how these quantum insights fundamentally redefine our understanding of reality, free will, and our own place within the cosmic tapestry. Prepare to have your deepest intuitions about objectivity and personal agency profoundly challenged. Hantoro. The universe is a mirror, your role in reality's formation. Let's revisit the idea that reality, at its most fundamental level, exists as a shimmering tapestry of possibilities until an observation or interaction forces it to choose a definite state. This isn't just some abstract philosophical musing. It's what experiments repeatedly tell us about electrons, photons, and all the other tiny building blocks of existence. Consider a quantum particle existing in a superposition, say spinning both clockwise and counterclockwise simultaneously. For centuries, our common sense told us it must be doing one or the other, even if we didn't know which. But quantum mechanics says no, it's genuinely doing both until something measures it, and the moment it's measured, it collapses into one definite state. Now, extend this concept. If everything at its core is made of these quantum particles, then the entire universe, before any observation, is a vast interconnected field of probabilities, a colossal superposition of all possible realities. This isn't just about a particle's spin, it's about the very arrangement of atoms that make up your chair, the trajectory of a distant star, the outcome of a coin toss, or even the weather tomorrow. They don't have a single fixed reality until, in some sense, they are observed. So if observation is key, what does that make you? Consciousness causes collapse, the ultimate act of creation. If the consciousness causes collapse interpretation holds true, and remember, it's a deeply debated but incredibly compelling idea, then your conscious awareness isn't just passively witnessing reality, it's actively participating in its formation. Imagine a world existing as an undifferentiated blur of potential, billions of possibilities for every single moment, every single particle, every single event. Then you come along, your eyes open, your mind engages. You think about something, focus on something, observe something. And in that very act, a specific reality clicks into place. The wave function collapses. The probability blur solidifies into a concrete outcome. This isn't to say that you can simply wish a chair into existence out of thin air. The possibilities are constrained by the laws of physics and the existing quantum potentials. But within that framework, your consciousness, by focusing attention, by making a choice, by observing, becomes the final arbiter of what is. Think about it. A quantum particle exists in a superposition of all possible locations until it's observed. If your consciousness is the ultimate observer, then the reality of that particle's location, indeed its very existence in a specific place, is, in a profound sense, brought into being by your awareness. This is where the title of our series truly resonates. If consciousness causes collapse, then your thinking, your attention, your decision to observe isn't just a reaction to reality, it's an intrinsic part of its creation. You're not just a spectator, you're a co-creator, constantly drawing specific outcomes from a sea of potential. This interpretation elevates the role of consciousness from a mere byproduct of brain activity to a fundamental active force in the universe. It suggests that without conscious observers, the universe might remain an amorphous cloud of probabilities, a symphony waiting for an audience to truly resonate. But what about the many worlds interpretation, MWI? If the wave function never truly collapses, and instead every quantum possibility causes the universe to split into innumerable parallel branches, where does that leave your agency? Are you still creating anything? In MWI, when that quantum particle is in superposition and you observe it, the universe doesn't choose one outcome. Instead, the universe splits. In one branch, you observe the particle spinning clockwise. In another, a different version of you observes it spinning counterclockwise. Both realities are equally real, and both versions of you are equally valid. Here, your consciousness isn't collapsing reality, it's experiencing one specific branch of an ever-diverging reality tree. Your choice or observation doesn't create the outcome, but it determines which path you, the observer, follow. Every decision point, every quantum uncertainty, every flicker of probability leads to a new split, creating an unimaginably vast multiverse. Does this diminish your free will? It's a fascinating question. On one hand, every possible outcome of your choice is realized somewhere by some version of you. If you choose to turn left, there's a version of you that turns right. Does that mean your choice wasn't truly free, since all possibilities are actualized anyway? On the other hand, you, the specific conscious entity experiencing this reality, are still making a choice. You are still deciding which branch you will inhabit, which specific narrative your consciousness will follow. Your agency isn't in creating the possibilities, but in navigating them, in forging your unique path through the multiverse. It's a bit like being the protagonist in an infinite choose-your-own-adventure book, where every choice you could make is made by a different version of you, but the choices you make still define your story. So while you might not be creating reality in the sense of bringing it into being from pure potential, you are certainly defining your reality, moment by moment, through your observations and choices, even if other versions of you are defining theirs differently. Regardless of which interpretation resonates more with you, one thing becomes undeniably clear. The classical notion of a single, objective, fixed reality existing independently of any observer is fundamentally flawed at the quantum level. For centuries we imagined the universe as a grand clockwork mechanism, set in motion by some divine hand, ticking away predictably, with every event predetermined. We were merely passive recipients of sensory data, our minds reflecting an external, unchangeable world. Quantum mechanics obliterates this comfortable illusion. It reveals a universe that is dynamic, participatory, and profoundly influenced by the act of observation itself. The world isn't just there, it's constantly emerging, constantly being defined in a delicate dance between potentiality and actuality. Your common sense, which is built on the macroscopic world of chairs and tables, simply doesn't apply at the subatomic scale. And if the foundation of everything is quantum, then the implications ripple upwards, challenging everything we thought we knew about the very nature of existence. If observation is the key to collapsing wave functions or to navigating the branches of the multiverse, then what becomes of your attention, your intention? Consider this. In a world of infinite possibilities, what you focus on might be what you bring into sharper relief, not in a magical manifest anything you want kind of way, but in a deeply scientific quantum mechanical sense. If your conscious attention is necessary to fix a particle's state, then the objects, events, and even ideas you direct your attention towards are arguably the ones that solidify into your experienced reality. This isn't about positive thinking making $1 million appear, though the link between mindset and outcome is a fascinating topic for another day. It's about the fundamental mechanism of reality. If reality is a probability blur, and observation brings it into focus, then what you choose to focus on is a powerful act of defining your world. It suggests that our internal world, our thoughts, our intentions, our awareness, is not separate from the external world, but intricately interwoven with it. The boundary between subject and object, between me and the universe becomes incredibly fuzzy, perhaps even non-existent at the deepest level. This perspective invites us to consider our thoughts and our attention not as mere internal processes, but as active participants in the ongoing creation of our perceived reality. Are you creating the universe by thinking? If your thinking leads to observation, and observation shapes reality, then the answer, in some profound sense, might be yes. As we peer deeper into the quantum realm, the lines between physics and philosophy, between science and spirituality, begin to blur in exciting and challenging ways. These aren't just abstract ideas for theoretical physicists. They have profound implications for how we live our lives, how we understand consciousness, and how we interact with the world around us. In our next chapter, we'll begin to explore some of the more practical and philosophical ramifications of this quantum revolution. What does a participatory universe mean for fields like medicine, technology, or even our understanding of free will and responsibility? How might these ideas reshape our societal structures, our ethical frameworks, and our personal worldviews? So keep those minds open and those questions flowing. The universe is far stranger and far more responsive than you've ever imagined. If you're enjoying this journey into the unknown, remember to hit that like button, subscribe to Dreamy Science for more mind-bending explorations, and drop a comment below. We love hearing your thoughts on these profound topics. Until next time, keep observing, keep questioning, and keep dreaming. Because in a quantum reality, your dreams might just be a blueprint for what's yet to be. Welcome back, truth seekers, to Dreamy Science. We've journeyed through the mind-bending landscape of quantum mechanics, from the ghostly dance of particles to the perplexing question of what an observer truly is. We've dared to challenge our deepest intuitions, moving from a universe of fixed certainties to one that shimmers with possibilities, a universe that might just be waiting for you to solidify its form. Last time, we grappled with the radical notions that consciousness might cause wave function collapse, actively solidifying reality from a blur of probabilities, or that our universe constantly branches into countless parallel realities, with our observations defining which path we experience. Both interpretations, consciousness causes collapse, CCC, and the many worlds interpretation, MWI, place you, the observer, at the very heart of existence. But what does this truly mean for your everyday life? Are you really creating the universe by thinking? Beyond the laboratory, your everyday reality, we've explored the bizarre behaviors of electrons and photons in controlled lab settings. But what about the chair you're sitting on, the screen you're looking at, or the coffee mug in your hand? These objects seem undeniably real, solid, and objective. They don't appear to exist in a probability blur until you look at them. So how do we bridge the chasm between the quantum weirdness of the subatomic realm and the seemingly stable reality of our macroscopic world? This is where the concept of decoherence comes back into play, but with a crucial twist. Remember how decoherence explains why macroscopic objects don't remain in superposition. It's because they are constantly interacting with their environment, with countless other particles, photons, air molecules, and even stray gravitational waves. Each of these interactions acts as a tiny, unconscious observation, effectively collapsing the wave function of the larger system. Think of it like this. A single electron might be in a superposition of spin up and spin down, but a chair is made of trillions upon trillions of atoms, each composed of electrons, protons, and neutrons. Each of these particles is constantly bumping into, interacting with, and exchanging energy with its neighbors and its surroundings. The sheer volume of these continuous pervasive interactions means that the chair's wave function is being relentlessly and instantaneously observed by the entire environment. It's not your single conscious glance that collapses the chair's state. It's the collective, continuous, unavoidable observation of the entire universe around it. So while the chair could theoretically exist in a superposition of being here and being over there at the quantum level, the moment it's formed and interacts with its environment, that superposition rapidly collapses. Its properties become definite almost instantly. This explains why we don't see chairs flickering in and out of existence or existing in multiple places simultaneously. Macroscopic reality appears stable because it's under constant universal observation by everything else. But here's the profound implication. Even if the environment is doing most of the heavy lifting, you are still part of that environment. Your eyes, your brain, your very presence contribute to this grand collective observation. You are not a passive spectator in a pre-existing reality. You are an active participant in its continuous solidification. The power of expectation, shaping probabilities. Now, let's circle back to the central question. Are you creating the universe by thinking? If our conscious observation plays any role, even a small one, in collapsing quantum possibilities, could our thoughts, our intentions, our expectations influence the probabilities of those collapses? This is where quantum mechanics touches upon some of the most profound philosophical and spiritual questions about reality. Imagine a quantum particle existing in a superposition of several possible states. Let's say it could be spin up, spin down, or perhaps even somewhere in between, each with a certain probability. When an observation occurs, one of these possibilities solidifies into reality. What if your focused attention, your strong belief, or your clear intention could subtly nudge those probabilities? Not to violate the laws of physics, but to favor one outcome over others within the existing probabilistic framework. This isn't about magic or wishful thinking in a simplistic sense. It's about a deeper, more subtle interaction. If consciousness is fundamental to the collapse and your thoughts are products of your consciousness, then it's not entirely unreasonable to hypothesize a connection. If the universe presents a shimmering tapestry of possibilities, and your consciousness is the needle that weaves one thread into definitive existence, what if the design you hold in your mind influences which thread is chosen? Consider the implications. If you consistently expect negative outcomes, are you, in some subtle way, increasing the probability of those negative quantum events collapsing into your reality? Conversely, if you cultivate a mindset of positive expectation, focus, and gratitude, are you subtly biasing the universe towards more favorable outcomes? This is a radical idea, one that pushes the boundaries of current scientific understanding and enters the realm of speculation. We don't have direct experimental proof that conscious intention can alter quantum probabilities in a measurable way for macroscopic events. The complexities of decoherence make it incredibly difficult to isolate such an effect. However, the very nature of quantum reality, probabilistic, indeterminate until observed, fundamentally participatory, opens the door to this line of thinking. It suggests that our internal world, our thoughts and feelings, might not be entirely separate from the external world. Perhaps they are intimately intertwined, two sides of the same coin in the grand scheme of reality creation, the multiverse of choice navigating possibilities. What if we lean into the many worlds interpretation, MWI? Here, the wave function never collapses. Instead, every quantum possibility becomes real, but in a separate, branching universe. When you make an observation or a choice, you don't collapse possibilities. You simply become aware of the specific branch of the multiverse you inhabit. All other possibilities continue to exist in parallel universes, with other versions of you experiencing them. In this scenario, you're not creating reality by thinking in the sense of solidifying it from nothing. Instead, you are navigating a pre-existing infinite landscape of realities. Your thoughts, your decisions, your focus, and your attention become the compass and rudder that steer your consciousness through this vast multiverse. If you consistently focus on a particular goal or outcome, are you, in a sense, aligning yourself with the branch of the multiverse where that outcome is realized? Are your thoughts not creating reality, but selecting which reality you experience? This perspective offers a different, yet equally profound understanding of the power of your mind. It suggests that every possibility you can imagine already exists, and your conscious self is simply experiencing one of those infinite paths. Your thinking becomes a form of active selection, a way of tuning into a specific frequency of reality. This doesn't mean that every fleeting thought instantly manifests. The sheer number of quantum interactions and the complexity of our macroscopic world makes such direct, instantaneous manifestation highly unlikely. But it does suggest that your consistent mental patterns, your deep-seated beliefs, and your sustained focus could play a role in shaping the trajectory of your personal experience within the multiverse. Consciousness, the ultimate enigma. Whether we consider CC or MWI, consciousness emerges as a central, almost foundational element of reality. But what is consciousness? For centuries, answers struggle to define it, to locate it, to understand its origins. Is it merely an emergent property of complex brain activity, an intricate dance of neurons and synapses? Or is it something more fundamental, a non-local phenomenon that precedes and perhaps even underlies physical reality? If consciousness is indeed involved in the collapse of the wave function, or in the navigation of the multiverse, then it might be far more than just a biological byproduct. It could be an intrinsic aspect of the universe itself, an active participant in the cosmic dance of creation and experience. This elevates the study of consciousness from a niche philosophical inquiry to a central quest in understanding the very fabric of existence. The measurement problem in quantum mechanics has, in a strange way, become the consciousness problem. Until we understand what consciousness is and how it truly interacts with the quantum realm, the full implications of a participatory universe will remain elusive. The participatory universe, a new paradigm. What quantum mechanics forces us to confront, regardless of interpretation, is the end of the purely objective mechanistic universe described by classical physics. We are no longer passive spectators observing a fixed external reality. Instead, we are active participants, intimately intertwined with the unfolding of existence. This new paradigm is one where reality is not out there, entirely separate from us. It is, in some profound sense, in here as well, a dynamic interplay between the observer and the observed, between consciousness and matter. The universe is not a clockwork mechanism ticking away independently. It is a living, breathing, responsive entity, and you are an essential part of its being. This understanding is both humbling and empowering. It's humbling because it reveals the vastness and mystery of what we still don't know. It's empowering because it suggests that your inner world, your thoughts, beliefs, intentions, and awareness holds a significance far greater than previously imagined. The question, are you creating the universe by thinking, might not have a simple yes or no answer. It's more nuanced, more profound. Perhaps you are not creating it from scratch, but rather actively participating in its manifestation, collapsing its probabilities, or navigating its infinite branches. This is not just science, it's a re-enchantment of the world. It invites us to look at our own minds, our own experiences, and our own place in the cosmos with a renewed sense of wonder and responsibility. But if our thoughts and consciousness truly hold such power, what are the implications for how we live our lives? How do we harness this understanding? And what happens when multiple conscious observers interact? Do our realities blend, or do we each exist in our own unique, self-created bubble? Join us next time on Dreamy Science as we delve into the fascinating concept of shared realities and the collective consciousness. Don't forget to hit that like button, subscribe for more mind-bending science, and drop a comment below with your thoughts on how your thinking might be shaping your reality. We love hearing from you. Welcome back, fellow explorers of the quantum realm. If you've been with us on this mind-bending journey, you'll know that in our last chapter we delved into the astonishing idea that your individual consciousness, your thoughts, your very act of observation might subtly influence the fabric of reality around you. Whether by nudging probabilities in the consciousness causes collapse model, or by selecting your path through the infinite branches of the many worlds interpretation, the passive observer is out and the active participant is in. But this revelation immediately sparks a profound question, doesn't it? If my consciousness is actively involved in shaping my reality, and your consciousness is doing the same for yours, then how do we ever experience a shared world? How do we all agree that the chair is solid, the sky is blue, and the laws of physics are generally consistent for everyone? Are we living in a multitude of personal overlapping dreams, or is there something more fundamental at play that unifies our experiences? This, my friends, brings us to one of the most intriguing and challenging aspects of quantum reality, the concept of a shared reality, and the tantalizing yet highly speculative idea of our collective consciousness. Let's revisit our familiar chair. When you look at it, it's undeniably there, solid and unmoving. When I look at it, it's the same. We both perceive the same chair in the same space. If, at the quantum level, the chair existed in a probabilistic blur of possibilities before our observation, how did our individual acts of observation, or the myriad observations from its environment, as decoherence suggests, conspire to create the same solid object for both of us? The key, as we touched upon in Chapter 7, lies in the sheer scale of interaction. While a single electron can maintain its superposition for a relatively long time in isolation, macroscopic objects like our chair are relentlessly bombarded by countless particles, photons, and environmental interactions every nanosecond. Each of these interactions acts as a tiny measurement or observation, constantly collapsing the chair's wave function into a definite state. The universe, in a sense, is constantly observing itself. So when you observe the chair, you're not pulling it from an entirely undefined quantum foam all by yourself. Instead, you're interacting with an object that has already undergone an astronomical number of decoherence events. This rapid and continuous observation by the environment ensures that the chair, and indeed most of our everyday world, appears stable and consistent to all observers. Our individual conscious observations are simply one more layer of interaction within an already incredibly complex and observed system. Think of it like this. Imagine a vast, intricate tapestry. Each thread is a quantum particle shimmering with possibilities, but the entire tapestry is constantly being touched, stretched and interacted with by an infinite number of tiny hands, environmental observations. By the time you come to look at a specific part of the tapestry, our chair, it's already largely woven into a consistent pattern. Your conscious observation might add a subtle nuance, perhaps solidifying a particular shade or texture for you. But the overall pattern is already a consensus reality established by countless prior interactions. But this doesn't fully answer the more subtle implications we discussed earlier. If our conscious thoughts can nudge probabilities or select specific branches in the multiverse, how do we reconcile these individual nudges and selections to form a truly shared experience? This is where the concept of collective consciousness enters the conversation, albeit on the very frontiers of scientific speculation and philosophical inquiry. If individual consciousness is a player in the quantum game, then what about the sum total of all consciousnesses? Could there be a larger, overarching field of awareness, a sort of cosmic mind that helps to establish the fundamental parameters and shared experiences of our universe? Imagine all human minds, perhaps even all sentient minds across the cosmos, interconnected at a deeper level than we currently understand. This isn't about telepathy or psychic powers, but about a more fundamental quantum-level interconnectedness. If our individual thoughts contribute to the collapse of wave functions or the selection of reality branches, then perhaps our collective thoughts, beliefs, and expectations form a kind of powerful consensus-generating super-observer. In this highly speculative view, the collective consciousness might be responsible for solidifying universal laws. Perhaps the very rules of our universe, the constants of physics, the fundamental forces, are in part solidified by a universal collective agreement or expectation. Establishing shared realities. While individual nuances might exist, the broad strokes of our shared world, the existence of gravity, the properties of matter, the flow of time, could be robustly established by the overwhelming observational weight of collective consciousness. Guiding probabilities. If individual thoughts can subtly nudge probabilities, then the collective beliefs and intentions of humanity, or all consciousness, could exert a more significant, albeit still subtle, influence on the trajectory of our shared future. Could widespread hope or despair, for instance, subtly shift the probabilities of global events? This is, of course, far beyond current scientific verification, but it's a fascinating thought experiment born from the implications of quantum mechanics. This idea resonates with ancient spiritual traditions that speak of a universal mind or a cosmic consciousness, suggesting that science, in its deepest explorations, might be circling back to profound insights once considered purely mystical. It's crucial to emphasize that these ideas about collective consciousness and its role in shaping reality are highly speculative, existing at the very edge of what physics can currently test. While quantum mechanics undeniably points to a participatory universe where observation is key, the leap from a particle's wave function collapse to collective human thought influencing global events is enormous and currently lacks direct empirical evidence. One of the biggest hurdles in exploring these concepts scientifically is what philosophers call the hard problem of consciousness. We still don't truly understand what consciousness is. Is it an emergent property of complex brains, a sophisticated biological computer, or is it something more fundamental, a basic ingredient of the universe as fundamental as mass or energy? If consciousness is a fundamental aspect of reality, then its proposed role in shaping that reality becomes much more plausible. But if it's merely an emergent phenomenon, then its ability to influence quantum events becomes far more difficult to explain. Without a clear scientific definition and understanding of consciousness itself, attributing it with the power to collapse wave functions, individually or collectively, remains a profound philosophical challenge. Physicists are still grappling with the measurement problem at the level of a single particle. Extending it to a global collective mind is a leap into uncharted territory. How do our two main interpretations, consciousness causes collapse, CCC, and many worlds interpretation, MWI, handle shared reality and the potential for the collective consciousness? In the consciousness causes collapse, CCC view, collective consciousness would act as a grand, unified observer. Our individual minds would contribute to a larger pool of awareness, and the collapse into a shared reality would be the result of this collective observational act. The chair is solid for everyone, because the collective consciousness of all sentient beings, or at least those in its vicinity, agrees on its solidity, constantly collapsing it into that state. Any individual nudges would be tiny ripples on a vast, collectively determined ocean. For the some many worlds. Interpretation, MWI. The concept of collective consciousness is trickier. In MWI, the wave function never collapses. Instead, every possibility is realized in a separate universe. So when you observe the chair, the universe splits into countless branches, one where you see a solid chair, another where you see a slightly different chair, and so on. Your consciousness simply experiences one of these branches. For a shared reality, we would have to imagine that our individual consciousnesses are constantly co-navigating or aligning into the same or very similar branches. Our interactions with each other cause our individual reality paths to converge, creating the illusion of a single shared world. Collective consciousness in MWI might then be understood as the emergent property of all these aligned conscious experiences, or perhaps a higher level structure that influences the probability of which branches are more likely to be experienced by multiple observers. Regardless of the interpretation, the profound implication remains: we are not passive spectators. Our very presence, our awareness, is deeply intertwined with the unfolding of reality. Whether we are actively collapsing possibilities or meticulously navigating a vast multiverse, we are integral to the universe's self-actualization. This journey through quantum reality forces us to abandon many of our deepest intuitions about the universe. The idea of a fixed, objective reality out there, independent of any observer, gives way to a dynamic, participatory, and fundamentally probabilistic universe. This isn't just a scientific curiosity, it's a profound philosophical and existential shift. If our consciousness, individually and perhaps collectively, plays a role in shaping reality, then our thoughts, our intentions, our beliefs, and our collective focus take on an entirely new significance. It suggests a universe that is not merely observed, but co-created. This isn't to say that simply thinking about $1 million will make it appear in your bank account, or that wishing for world peace will instantly manifest it. The universe, even at the quantum level, operates with immense complexity, and decoherence ensures the stability of our macroscopic world. But it does open the door to considering that our internal states, our focused attention, our deeply held beliefs, our collective aspirations, might have a more subtle, yet fundamental influence on the probabilities and possibilities that manifest in our lives and in our shared world. We've moved from a universe of rigid clockwork to a shimmering tapestry of possibilities, where the act of looking, of thinking, of being aware helps to draw out the patterns that we call reality. It's a universe that invites us not just to understand it, but to participate in its ongoing creation. What an incredible journey, isn't it? From the bizarre dance of electrons to the potential for a collective cosmic consciousness, quantum reality challenges us to rethink everything we thought we knew. The questions are far from settled, and the scientific exploration continues. But one thing is clear: The universe is far stranger and far more intimately connected to our consciousness than we ever dared to imagine. As we continue to explore these mysteries, we invite you to keep pondering these profound questions. How do your thoughts shape your world? How might our collective thoughts shape our world? The answers perhaps lie not just in physics labs, but within the very depths of our own awareness. Join us next time as we delve even deeper into the practical and philosophical implications of this participatory universe. Until then, keep dreaming big, keep asking questions, and keep exploring the infinite possibilities of quantum reality. Don't forget to hit that like button, subscribe for more dreamy science, and drop a comment below with your thoughts on shared reality and collective consciousness. What do you think? Welcome back to Dreamy Science, where we continue our journey into the most profound mysteries of existence. We've navigated the strange waters of quantum mechanics, where particles shimmer into being only upon observation, where reality itself seems to be a shimmering tapestry of possibilities until we look. We've grappled with the measurement problem, which, as we saw, quickly transforms into the consciousness problem. Is consciousness the ultimate observer, collapsing wave functions and solidifying reality, CCC? Or are we merely navigating one branch of an ever-splitting multiverse, our choices defining our path through infinite possibilities, MWI? In our last chapter, we touched upon the idea of a shared reality, how the continuous collective observation of environmental decoherence gives us a consistent world, and even speculated about the intriguing, albeit highly speculative, concept of a collective consciousness. But now we want to bring it closer to home. We want to ask the question that has been implicitly woven through every chapter. What about your role, not just as a passive observer, but as an active participant? What about the power of thinking? For centuries, science has largely operated under the assumption that our thoughts, our inner world, are separate from the external objective universe. The universe just is, and we as conscious beings merely perceive it. But what if quantum reality suggests a more intimate, more dynamic relationship? If the act of observation, even an unconscious interaction with the environment, can collapse a wave function, transforming a probabilistic blur into a concrete reality, then what about our conscious intention? What about our focused attention? Is there a difference between simply seeing something and actively intending for something to be a certain way? Let's rewind to the double-slit experiment for a moment. Remember how the electrons, when not observed, behaved like waves, creating an interference pattern. But the moment we introduced a detector, even just to know which slit they went through, they behaved like particles taking a definite path. The knowledge or the act of gaining information seemed to be the key. Now consider this. What if that knowledge isn't just a passive recording, but an active shaping? Imagine you're standing before a quantum coin. Before you look, it's in a superposition of both heads and tails. It's a probability blur existing as a potential for either outcome. When you look, it collapses to one or the other. But what if, before you look, you strongly intend for it to be heads? Does your intention, your focused thought, subtly nudge the probabilities before the collapse? Does it increase the likelihood of one outcome over another? This is where we move beyond just observation and delve into the fascinating, albeit speculative realm of conscious creation. If consciousness is indeed fundamental as the consciousness causes collapse, interpretation suggests, then it stands to reason that the quality of that consciousness, its focus, its intention, might matter. Think about it from a slightly different angle. If the universe is a shimmering tapestry of possibilities, as we've often described it, then perhaps our consciousness is not just a light illuminating one thread, but a needle weaving new patterns. Our thoughts, our beliefs, our expectations, are these the threads we use to weave our personal reality from the quantum fabric? This idea challenges our deepest intuitions about free will and determinism. For a long time, classical physics painted a picture of a clockwork universe where every event was predetermined by prior causes. Free will in such a universe would be an illusion, but quantum mechanics, with its inherent randomness and the role of observation, throws a wrench into that clockwork. If the future is not fixed, if it exists as a set of probabilities until observed, then perhaps our choices, our intentions, our thinking are the very mechanisms by which we select our path through those probabilities. Consider the hard problem of consciousness, the baffling question of how physical matter gives rise to subjective experience, to qualia, to our inner world of thoughts and feelings. Many physicists and philosophers are beginning to suggest that perhaps consciousness isn't an emergent property of complex brains, but rather a fundamental ingredient of the universe, just like space, time, and energy. If consciousness is fundamental, then its interactions with the quantum realm might be far more profound than we currently understand. Could our brains, operating at a quantum level, be more than just biological computers? Some theories, though highly controversial and still largely unsubstantiated, propose that quantum processes within the microtubules of neurons could be the seat of consciousness, allowing for non-local connections or active engagement with the quantum field. While this remains in the realm of theoretical physics and speculative neuroscience, it opens a door to the possibility that our very thoughts are not just biochemical reactions, but quantum events with the potential to interact with the underlying fabric of reality. Let's be clear. We're not suggesting that you can simply think $1 million into your bank account or will yourself to fly. The macroscopic world, as we discussed, is subject to pervasive environmental decoherence. The sheer number of particles and their constant interactions mean that any quantum superposition quickly collapses into a classical state. Your chair is a chair, not a superposition of a chair and a teacup, because countless photons, air molecules, and gravitational fields are constantly observing it, forcing it into a definite state. The consensus reality we share is incredibly robust. However, what if the influence is more subtle? What if in that vast shimmering tapestry of possibilities, our thoughts and intentions can subtly bias the probabilities in our personal quantum bubble? Imagine a situation where multiple outcomes are genuinely possible in your life. Say, getting a new job or meeting a particular person or finding a solution to a problem. If your consciousness is actively engaged in shaping reality, could your focused intention, your unwavering belief, subtly increase the probability of your desired outcome manifesting within the bounds of what is physically possible and within the context of shared reality? This isn't magic, it's a reinterpretation of causality in a participatory universe. If reality is truly probabilistic at its core, and if consciousness plays a role in solidifying those probabilities, then perhaps our conscious focus is a mechanism for selecting from the available quantum potentials. Your thoughts then become less about creating something from nothing, and more about selecting from an abundance of possibilities. Think about the placebo effect. It's a powerful demonstration of how belief and expectation can profoundly impact our physical reality. When a patient believes a sugar pill is medicine, their body often responds as if it were real medicine, sometimes even curing serious ailments. While we understand some of the neurochemical pathways involved, the underlying mechanism of how a thought, an expectation, can trigger such profound physiological changes remains a source of scientific wonder. Could it be that our conscious belief is interacting with the quantum field of our own biology, nudging the probabilities of cellular function and healing into a desired state. This leads us to a profound philosophical shift. If our thoughts and intentions truly participate in the manifestation of reality, even in subtle ways, then our responsibility for our experience takes on an entirely new dimension. We are no longer passive recipients of a predetermined fate, but active co-creators, weaving our personal realities from the raw material of quantum possibilities. This perspective encourages us to cultivate a deeper awareness of our inner landscape. What are we thinking? What are we expecting? What are we intending? If these internal states are not merely epiphenomena but active forces, then the quality of our thoughts becomes paramount. Positive expectations, clear intentions, and a belief in favorable outcomes might not just be good for our mental health. They might be subtle tools for shaping the probabilistic quantum field around us. Of course, this is not to say that every thought instantly manifests. The universe, as we've established, is a complex dance of countless interacting quantum fields, governed by laws we are only beginning to comprehend. Our individual consciousness is part of a larger interconnected web. But the very existence of quantum mechanics, with its observer effect and the inherent indeterminacy of reality, compels us to reconsider the traditional boundaries between mind and matter. The journey we've taken through wave-particle duality, superposition, entanglement, and the measurement problem has fundamentally challenged the notion of an objective independent reality. It has pushed consciousness from the periphery to the very center of our understanding of the cosmos. And now, as we contemplate the implications, it beckons us to consider the active role of our minds, our thinking, in this grand, ongoing creation. So, are you creating the universe by thinking? The most honest scientific answer is, we don't fully know how or to what extent, but the evidence from quantum mechanics strongly suggests that your consciousness is not a mere spectator, but an active participant in the unfolding of reality. The universe doesn't just exist independently, it seems to be in a constant state of becoming, and you, with your thoughts, your intentions, and your attention, are part of that becoming. This realization isn't just a scientific curiosity, it's an invitation to a new way of living, a new understanding of our agency, and a profound appreciation for the power of the mind. It challenges us to look inward as much as we look outward, recognizing that the universe might be mirroring back to us the very patterns we hold within. As we continue to explore this fascinating frontier, we'll delve even deeper into the practical implications of this participatory universe. How can we consciously engage with this quantum reality? What does it mean for our personal growth, our collective future, and our understanding of what it means to be human? Join us next time on Dreamy Science as we continue to unravel these mind-bending questions. If you're finding this exploration as intriguing as we are, hit that like button, subscribe for more deep dives into scientific wonder, and drop a comment below with your thoughts on the power of intention. We love hearing from you.